Good morning, students. Today we are going to discuss about the third class of the capacitors. In the last class, we discussed about the different types of fixed capacitors, properties of the fixed capacitors, and specifications of the fixed capacitors we discussed in the last class. Today class we are going to discuss about the variable capacitor. Another class general classification is we have the two type of capacitors are there, fixed capacitors and variable capacitors. We already discussed about the fixed capacitor, the capacitors which having the fixed values in any circuit. We don't change the values of the capacitor. Coming to the second classification, that is the variable capacitor. The variable capacitors are the capacitor. The capacitance value may be varied from particular range. We can change the value. Generally, where we use this type of capacitors means sometimes we require to use the different capacitor at a particular point. So in the circuit connection we if you wanted to add capacitors and removing another value, putting another value, if you wanted to check the different capacitance values, it is difficult to place the new value and removing that one, placing another one value. Instead of placing all these, we use the variable capacitor. The variable capacitor having the particular range of values are there. We can use this set of different capacitor values for our application without adding and removing the capacitor values. That is the advantage of variable capacitor. So now we having the variable list of variable capacitor. You can see air, polystyrene capacitor, mica, trimmers, padders, air trimmers. These are the different types of variable capacitors: air, polyester, mica trimmers, padders, and air trimmers. We are having the. So now the symbol of the variable capacitor is, it is the simple as usual the capacitor diagram, and we having the variable arrow is there. So this is the symbol of the variable capacitor. So variable capacitors, if you having this one, so in the variable capacitor we having the air polystyrene variable capacitor. The range and properties of the variable capacitor now we going to study. The first one is the air polystyrene variable capacitor. The capacitance range is 15 picofarad to 500 picofarad. The meaning is the value is changes from the 15 picofarad to the 500 picofarad. The tolerance is 1000% and the power factor is 1000. Maximum working voltage is 1000 volts. The variable capacitor is worked maximum of 1000 volts. The operating temperature is 80 degrees centigrade, and this is used in tuning circuits of receivers and transmitter. Generally in the radios and some sort of circuits we need the tuning circuit. The tuning is performed by using this type of air polystyrene variable capacitors. This is a one type of variable capacitor. Properties: air polystyrene variable capacitor. The range is 15 picofarad to the 500 picofarad. Tolerance is 1000%. Power factor is 1000. The operating voltage is 1000 volts. Operating temperature is 80 degrees centigrade, and this is used in tuning circuits of the receivers and transmitters. The next one is the mica trimmers. Mica trimmers. The trimmers means next one is the mica trimmers. So mica trimmers are the capacitors which having the value of mica trimmers. The capacitance range is 4 picofarad to the 70 picofarads. The meaning is the variable capacitor can having the values from 4 to 70 picofarad. If you change the value, we can get the 4 to. The maximum working voltage is 500 volts. The operating temperature is 80 degrees centigrade for the mica trimmers. These are used in tracking and alignment of radio receiver circuit. In the radio receiver circuit, for providing the alignment, this type of mica trimmers are used. Padders. So padders are also some sort of variable resistors. These padders are the capacitance range of the padders is 100 picofarad to the 600 picofarad. The maximum working voltage is 500 volts. Operating temperature is 80 degrees centigrade. The padders are used in tracking and alignment of radio receivers as previous trimmers. Now we are going for the another variable capacitor, that is a air trimmers. Air trimmer having the capacitance range is 8 picofarad to the 100 picofarads. Maximum working voltage is 500 volts. Operating temperature is 80 degrees centigrade. These are used in tracking and alignment of the radio receiver circuit. So these are the different types of variable capacitor which having the variable range of the capacitance. So now we try to discuss about the general application of capacitors, where we are using the capacitors. General applications of capacitors. The capacitors are used generally to store the electrical charge. The first one is to store the electrical charge. Simply we can say that battery type structure. The big capacitor will store the energy, electrical energy in the electrolytic field, or you can also call it as electrostatic field. And these capacitors are used to block the DC and allowing the AC. Generally in the filter circuit or in the rectifier circuit, what we are using is the AC current is converted into the DC current. So here in the rectifier, what we are getting is we are getting the pulsating DC, that is the DC contained some portion of the AC. So by using the capacitor, we try to remove those unwanted AC components. So capacitor having the property that if we connect the capacitance, the capacitor will allow the AC signal and blocks the DC signal. So in the rectifier, what we are doing is capacitor is used as a bypass element which bypasses the AC component to the ground. Like that we eliminate the AC components in the pulsating DC circuit. This is also called as a filtering element. The capacitors are used in electronic oscillator circuit. Generally, for For the oscillations, we require the tank circuit. In the tank circuit, we having the one inductor and one capacitor is there. Whenever these reactances of inductor and capacitance are equal, then there occurs the resonance. At that position, the frequency or oscillations may be generated. So because for this type of matching, what we are doing is we use the capacitor and we tune the capacitor such that the circuit should generate the oscillations, and it is also used in tuning and tracking circuits in radio receivers. In the radio receivers, we use the capacitor to match the frequency of the receiving signal. Whenever capacitance and inductor reactances are matches, it goes into the resonance. When it is resonance, what happens means the circuit becomes short circuit. Whatever the signal is there, that signal is passes into the receiver circuit. At that position, we use the capacitor. And this capacitor used in filter circuit, as I already mentioned, capacitors blocks the DC and allows the AC. So in the filter circuit, we try to block the DC components by using the capacitor, and also used for power factor in AC circuit. In the AC circuit, to provide the proper power factor, we use the capacitor. Once again, you see, we already discussed about variable capacitor. The capacitor whose capacitance can be varied is called as a variable capacitor. Already we discussed in the last slide, if the capacitance can be varied, that is called as a variable capacitor. You can see the symbol of variable capacitor. Based on the application, they are divided into the two type of capacitor. First one is the tuning capacitor, second one is the trimming capacitor. The variable capacitors are divided into two types. First one is the tuning capacitor, second one is the trimming capacitor. So what are the tuning capacitor? Now we try to discuss about the tuning capacitors. You can see, once you see the points, what are the points regarding the tuning capacitor. The capacitance value is varied frequently and continuously. That type of capacitors are called as a tuning capacitor. The meaning is, in our application, if the capacitance value is varied frequently and continuously, then we use the tuning capacitor. Generally, the resonant frequency can be varied by varying the capacitance. In the circuit where we are using this capacitor means, to get the resonance frequency, we vary the capacitance value. That type of circuits are called as a tuning capacitor. So these used for tuning the radio and TV receivers to select the different station. To select the TV and radio station, we use the tuning capacitors. These are either air or dielectric variable capacitor. Air or dielectric variable capacitor. The meaning is, here we use the dielectric as a air or dielectric material. So next capacitors are the trimming capacitor. You know that what is the tuning capacitor means? Tuning capacitor means where we used means The tuning capacitors are nothing but where the capacitance value is varying continuously and frequently, where the capacitance is used to tune the resonance frequency, where the capacitance is used to tune the radio and TV receivers, where the capacitance is used air or dielectric. These type of capacitors are called as a tuning capacitors. The next capacitor is the trimming capacitors. Trimming capacitors are trimmers. We can also call as a trimmers. If the capacitance value is varied less frequently, if the capacitance wherever you varying the capacitance value less frequently at rare times, if needed we use this type of thing, that type of are called as a trimming capacitors. Trimmers are put in parallel with the tuning capacitors. These trimming capacitors are used parallel with the tuning capacitors are fixed capacitor in electronic circuit. Trimming means it try to vary small amount of voltages, a small amount of capacitance values. These are used for tracking and alignment of receivers. Tracking and alignment of receivers, we are using this. Types of trimmers depends on dielectric we used. The types of trimmers depends on the what type of dielectric we are using, that is called as a trimmers. You already understand that trimming capacitor are trimmers. So wherever less frequently varies the capacitance, that type of circuit is called as a trimming capacitor. These trimming capacitors are connected parallelly with the tuned capacitors or fixed capacitors. So that type of capacitors are called as a trimming capacitors. So now we are going to discuss about another topic, that is losses in the capacitors. What are the losses in the capacitor? If you have any component, the component must have some sort of losses are there. The capacitor having the some of the losses. First one is the leakage resistance loss, leakage resistance loss, absorption loss, absorption losses, power factor loss. These three type of losses are there. Now we try to discuss in detail about these losses in the capacitor. Leakage resistance loss, absorption losses, power factor losses. Leakage resistance loss. What is the leakage resistance? Already we discussed. These leakage resistance is caused by small leakage current through the dielectric across insulated case between terminals of the capacitor. This is occurred because some sort of current is passes through the dielectric material, or some sort of current is formed some closed loop paths on the dielectric material. That type of leakage is called as a leakage resistance. After a long period of time, the charge on capacitor will be neutralized by leakage current due to leakage resistance. The meaning is this is caused by small leakage current through the dielectric across insulated case between terminals of the capacitor. After a long period of time, the charge on capacitor will be neutralized by leakage current due to leakage resistance. So another losses are absorption losses. So what are the absorption losses? You know, absorption means it is absorbing. Absorption losses. The capacitor plates do not charge or discharge with the same rate as the frequency of the applied AC voltage. Difference between AC voltage applied and AC voltage stored in the dielectric due to absorption loss. The meaning of absorption is, so whenever we are charging the capacitor with the AC charge, the charging is may not equal to the frequency of the our supplied voltage. The charging frequency and the discharging frequency may have the difference. That difference is called as the absorption loss. The meaning is that amount of energy is lost because of the absorption of the capacitor. So this type of losses are called as a absorption losses. Next one is the power factor. So what is the power factor? Means fraction of input power dissipated as heat loss in the capacitor. The meaning is, if the energy is dissipated as a power, that is indicated in the form of the power factor loss. Power factor of input power dissipated as heat loss in the capacitor. The power factor depends on the dielectric and it is independent of capacitance value or voltage rating of the capacitor. The reciprocal of the power factor can be considered as a quality factor. The quality factor Q equals to 1 by power factor. The lower the numerical value of the power factor, the better is the quality factor of the capacitor. So the thing is, power factor indicates the loss, the heat loss dissipated at the capacitor. So these are the three losses. First one is the leakage resistance loss. Second one is the absorption losses. Third one is the power factor losses. We need to know and we need to minimize this type of losses in the capacitor. Now, so representation of the capacitor with its losses, that is, you can see, so it is a capacitor we having the ideal capacitor C without having any losses. Here we having the two types of losses, that is absorption loss, second one is the leakage resistance RL. So practically these two are negligible. We can simply take as a simple capacitor. If you take perfect representation of the capacitor, means the ideal capacitance with the series with the absorption loss and parallel with the leakage resistance. This is the representation of the capacitor with the losses. Once you can see and try to understand what is in the circuit diagram. Ideal capacitor, absorption loss resistance and the leakage resistance. Absorption loss is connected with the series and the leakage resistance is connected with the parallel. Okay, next we try to discuss about the combination of capacitors. So combination of capacitor means how we can connect the capacitor in series or in parallel or in series with the parallel. So what happens, how we can calculate these equivalent capacitance of these capacitors whenever you connected in different forms. Now we try to discuss about the combination of the capacitors. Capacitors may be connected in series to decrease the total capacitance value. Capacitors may connected in parallel to increase the total capacitance value. If you wanted to decrease the capacitance value, what we need to do is, if two capacitors are connected in series, the value will be reduced. If two capacitors are connected in parallel, the value of the capacitance value is increases. So now we try to discuss what happens when we connect in series and parallel. Capacitors are connected in series. What happens? Two or more capacitors connected in series. The total capacitance is decreases. This is exactly opposite to the resistors. If two or more resistors connected in series, the resistance value increases. But coming to the capacitors, if two or more capacitors are connected in series, the total capacitance is decreases. It has the effect of increasing the distance between the capacitor plates. What happens? If you connect it in series, it has the effect of increasing the distance between the capacitor plates. The total capacitance is less than the lowest capacitance present in the circuit. If in the circuit, if 10 or 15 capacitors are connected in series, if anyone having the lowest value, the total capacitance is less than that lowest capacitance present in the circuit. These are the properties of the capacitors connected in series. Now we try to discuss about the capacitors connected in series. We try to solve the problems. You can see. So three capacitors are connected in series end to end. So series connection means one capacitor having the two terminals. The second terminal of the one capacitor is connected to the first terminal of the another capacitor. You can see the capacitors are connected. First one, second, three capacitors are there. Capacitance are in series connected C1, C2, C3. Capacitance of three capacitors. You can see. So here the voltage we are applying is this is a series means the voltage is divided. The first capacitor having the V1, the second capacitor having the V2, third capacitor voltage drop is V3, and the first capacitor charge is Q1. Second, this is because it is this series, so the charge in the circuit is same. The charge in the circuit is same, so that is the Q. Charge is same, but the voltage drop is different. V1, V2, V3. So now we try to discuss the calculation. V1, V2, V3 voltage drops across the C1, C2, C3. C1, C2, C3 capacitance of three capacitors. V is the applied voltage. So this is the thing. Now we try to analyze the circuit. In series combination, charges Q on all capacitor is same. We already discussed. In the series, the charge is same, but voltage drops are different. If we applied the KVL to the circuit, what the Kirchhoff voltage law says that sum of the voltages in any loop is equals to the 0. Sum of the voltage is equal to 0, or the applied voltage is equal to the sum of voltage drops in the circuit. It states that Kirchhoff voltage law. By using the Kirchhoff voltage law, you can see in the circuit we can apply the positive and negative indications. When the applied voltage having the positive terminal and negative terminal, from the positive terminal the charge is moving and reaches to the negative terminal, so the charge entering always we treat it as the plus. That is the first one is the V1, first terminal is the plus V1, second terminal first is the positive, and third is the positive terminal, as we mentioned in the circuit diagram. So because of by using the Kirchhoff voltage law, we having the voltage equals to the supplied voltage equals to the sum of the drops in the circuit, that is the V1 plus V2 plus V3. So that is, we know that the voltage across the capacitor is the total voltage equals to the total capacitance equals to the total charge by applied voltage. C is equal to Q by V. Already we know that total voltage V equals to charge by capacitance. The total charge by total capacitance. You know that in the series circuit, the charge is same. The charge is indicated as a Q. So now I am substituting the total voltage V equals to Q by C as in the equation. Coming to the V1 and V2 and V3. So V1, V2, V3s are three different voltage drops across the three different capacitors. The three different capacitors having the different capacitance of C1, C2, C3, and the different voltage drops are V1, V2, V3. But the charge on the three capacitors are same, Q, Q, Q. So now I am substituting the voltage drop V1, V2, V3 in terms of charge and capacitance. The first capacitance voltage drop is Q by C1 because charge is same Q. C1 is the capacitance of the first capacitor, Q by C1. The second one is the Q by C2. Third one is the Q by C3. So now we can get the final equation that the total capacitance of a circuit, series circuit, is 1 by C total capacitance equal to 1 by C1, 1 by C2, 1 by C3. If we having the n number of capacitors are connected in series, then the equation is 1 by C total equals to 1 by C1, 1 by C2, 1 by C3, so on 1 by Cn. So that's why n number of capacitors connected in the circuit also we can calculate the value of the capacitance. So now we try to calculate the one example of the circuit which is connected in series. The first one is so the question is, when 8 microfarad, 2 microfarad and 16 microfarads are connected in series, find out the total capacitance. So we given the series connection, so we need to use the series equation. We given the three capacitors, 8 microfarad, 2 microfarad, 16 microfarad. So first the total capacitance equal to 1 by C1 plus 1 by C2 plus 1 by C3. 1 by C total equal to C1, you know that 8 microfarad, all are in microfarad. So at last we use this microfarad. 1 by 8 plus 1 by 2 plus 1 by 16. The total value is, if you take the LCM, we get the 11 by 16. Now from this equation, the total capacitance is equals to 1.454 microfarad. Like this, we can calculate the series capacitance very easily by using this series capacitance equivalent equation. So next, again we try to do the second example. So this is somewhat a different one. That is, already you know that in the series the charge is common and the capacitance are different and the voltages are different. So if we know the charge, we can find the V1, V2, V3. Already we know the C1, C2, C3 because by default the capacitor having the capacitance values. So now the problem is like that. Three capacitors of 10 microfarad, 50 microfarad and 25 microfarads are connected in series. Find the total capacitance and the charge on it when connected to a 230 volt supply. So what is the meaning is, once again I read the question, that is three capacitors of 10 microfarad, 50 microfarad and 25 microfarad are connected in series. Find the total capacitance and the charge on it when connected to a 230 volts supply. So the meaning is he asking about the total charge when we connected in series. He asking about the total charge and also asking about the total capacitance. He already given the total applied voltage is 230 volts. The given data is C1 equal to 10 microfarad, C2 equal to 50 microfarad, C3 equal to 25 microfarad and the applied voltage is 230 volts. Then you find the C value and Q value. We know that the total capacitance value in the series is 1 by C total equal to 1 by C1 plus 1 by C2 plus 1 by C3 as shown in the equation. We substitute the C1, C2, C3. C1, C2, C3, if you substitute there, we will get the total capacitance value is 6.25 microfarad. The total capacitance is the 6.25. Now we need to find the charge Q. Already you know that in the series charge is same. So the total capacitance formula is total capacitance is equal to generally Q by V. If you wanted to know the charge equal to C into V. We know the C and we know the V. Then the value is C is the 6.25 microfarads and the V is 230 volts. The answer is the charge is 1.43 microcoulombs. The answer is 1.43 microcoulombs. Like this, if we know the capacitance and the applied voltage, we can easily find the charge which is passing through the circuit. That is the charge of the circuit. This is the another type of example. Next, another example you can see. This is another one. So this type of capacitor is same formula, but we try to finding the, that is we having the two capacitors having capacitance of 10 microfarad and 15 microfarad respectively are connected in series across a 200 volts DC supply. What he says that two capacitors 10 microfarad 15 microfarad connected in series, and he also given the applied voltage 2 volts. What he asking is charge on each capacitor. You know that in the series charge is same each and every capacitor. You know already we find the potential difference across the each capacitor. This is the new one. We try to find the potential difference across the each and every capacitor. If you know the charge, that is nothing but a C is equal to Q by V. If you know the capacitance and the charge, we simply find the voltage V. V equal to Q by C1. V equal to Q by C1. Like that we can find. So once again you see the problem. Okay. So now we try to find the solution. So what are the given data you try to see? The given data is C1 equal to 10 microfarad, C2 equal to 15 microfarad. The applied voltage is 200 volts. What we needed? We need the total charge. We need the voltage drop across the different capacitors. The first one V1 and V2. So already we know that series capacitance formula. The 1 by total capacitance equal to 1 by C1 plus 1 by C2, because we are having only two capacitors. So 1 by C equal to 1 by 10 microfarad, 1 by 15 microfarad. The total capacitance is 6 microfarad. The total capacitance is 6 microfarad. If you know the total capacitance, we need to know total charge. In the series, charge is same. The charge equal to formula is Q equal to C V. Already we know the C equal to Q by V formula. You know the V and you know the C. So the total value V is Q equal to 1.2 millicoulombs. 1.2 millicoulombs. Now we try to find the individual voltage drop V1 and V2. We already know that the potential difference across each capacitor, since charge is the same in series circuit, so the voltage drop V1 equals to Q by C1. You know the Q value and C1 value. So the value is 1.2 into 10 power minus 3 by 10 into 10 power minus 6. We get the 120 volts. First V1 voltage drop, first capacitor voltage drop is 120 volts. Second voltage drop is Q by C2. You know the Q value and C2 value. If you substitute, that is 80 volts. So the total is 120 and 80, 200 volts supplied voltage. Like this, we need to calculate the total charge and total voltage, and we also find the individual voltages in the series circuit. This is about the series connection of the circuits. So now we are going to discuss about the another connection, that is a capacitors are connected in parallel. So this is the another type of connection. So this is called as a parallel connection. If two or more capacitors are connected in parallel, the capacitance is increases because it has the effect of adding the plate's area. What it makes that it adds the plate area. So that's why the capacitance is increases in parallel connection. Therefore, the total capacitance is the sum of the individual capacitances. Sum of the individual capacitance. Coming to the in the series, what happens? The distance between the plates are increases. The effect it shows that the distance between the two plates are increases. Coming to in the parallel connection, the capacitor plate area is increases. When the capacitor plate area increases, automatically the capacitance value is increases. So if the two or more capacitors are connected in parallel, the capacitance value is increases because it has the effect of adding the plate areas. Therefore, the total capacitance is the sum of individual capacitances. So 3 capacitor, if you connected in series, you can see 3 different capacitors, C1, C2, C3. Parallel means both the leads are connected at the same position. So these first and second is connected first at the first, second at the second we are connecting. So that's the type of this connection is called as a parallel connection. That is a C1, C2, C3 capacitance of 3 capacitors Q1, Q2, Q3 in the parallel. The charge is different, the voltage is same, but the charge is different. In the series, the charge is same, voltages are different. The voltage drop of the individual capacitor having the individual voltages, but in the parallel, the total voltage is same as the applied voltage. The change is charge is the different Q1, Q2, Q3. So when you can see potential differences across each capacitor is same, but the charge on the each capacitor is different. Just like the Kirchhoff current law, sum of the currents equal to 0, or sum of entering currents equal to sum of leaving currents. We having them sum of total charge equals to sum of distributed charges. That is the Q equals to Q1 plus Q2 plus Q3. That is, the potential difference across each capacitor is same, but charge on each capacitor is difficult. That is, the charge equals to Q1, Q2, Q3. That Q already you know, the Q equal to capacitance and voltage CV. So C1V plus for the second one C2V, third one C3V, the voltage is same. So if you cancel the voltages, the total capacitance in the parallel combination is C equal to C1 plus C2 plus C3. If we having the n number of capacitances, that is C equal to C1 plus C2 plus C3, so on Cn. So this is the parallel combination of the capacitors. Now we try to do some problems on the parallel connection. So first one is the capacitance 10 microfarad, 20 microfarad and 5 microfarads are connected in parallel. Find the total capacitance. Find the total capacitance. He given is parallel connections. Parallel, the total capacitance equal to C1 plus C2 plus C3. So already we know that 10 microfarad, 20 microfarad, 5 microfarad. The total capacitance is 35 microfarad. This is the one type of problem. The next type is so what he asking is total capacitance and charge on the each capacitor. So you know that in the parallel connection we having the different charges. He asking the charge on each capacitor. 3 capacitors are there with the capacitances of 10 microfarad, 15 microfarad and 25 microfarad and joined in parallel across the 250 volt DC supply. Then calculate the total capacitance value and charge on the each capacitor. You know that what we know that we only know that these are connected in parallel. The given data is given C1, C2, C3 values and the applied voltage. We need to find the C value, total capacitance value and charge Q1, Q2, Q3 values. So now we know the formula. Total capacitance equal to C1 plus C2 plus C3. The total value is 85 microfarad. So in parallel circuit, charge is same. So the charge is different. The voltage is same. So the Q1 equal to C1V, Q2 equal to C2V, C3 equal to C3V. We know already C1 value, V value, C2 value, V value, C3 value, V value. If you substitute there, we can find the Q1 charge, Q2 charge and Q3 charge. Like this, we can find the total capacitance of the parallel circuit. So this is the end of our class regarding the capacitors. So we discussed in this class so different types of variable capacitors and properties of the variable capacitor we discussed, and combination of the capacitors with whether how they are connecting. If they are connected in series, what is the total capacitance? If the capacitors are connected in parallel, what is the total equivalent capacitance? For that we find the different formulas, and also we exercise the different problems on the two types of circuit, series connection and parallel connections. Thank you.